Data independence was one of the key goals of the original design of the relational model back in the late 1960s, and the key idea was to insulate applications from the structuring of the data. Data independence was refined shortly after it was defined into two separate categories. Logical data independence is the idea that views should be able to be maintained, which is to say they should stay the same, even if the logical structure, even if the schema of the database changes. So for example, if I were to add a column to a table, or if I were to take a table and split it into two tables, we should be able to hide that from the queries above by introducing appropriate views. Physical data independence is the idea that the logical structure, the schema, should remain the same even when the physical structure or the physical schema changes. So adding B trees or reorganizing the order of a heap file should not affect the queries up above. It should only affect their performance. So these levels of abstraction fit into our stack here. Logical data independence is that separation between views and the conceptual schema. We want the views to stay the same even if we change the conceptual schema. Physical data independence is the separation between the conceptual and physical schemas. We'd like to keep the same conceptual schema even if we have to reorganize data underneath in the physical schema. And I would say in general that physical data independence is used all the time. It's a key aspect of relational databases. Logical data independence is also quite prevalent and is particularly helpful with things like access control, where you're trying to hide detailed information from some users and allow it to others. So, why is data independence sort of a database thing? Why is it particularly important for database management systems? The answer is that databases and their associated applications persist over long periods of time. So at this point, I like to tell a little anecdote about my mom. My mom is the bomb. She was a systems analyst, which is the word they used back then for a software engineer, back in the 1960s, the 70s, the 80s, into the 90s. And she worked for big state organizations and the state university writing database programs in languages like COBOL and SQL once it was invented back in the day. And my mom was real good at what she did. And at some point she retired and she got a call from some of her former colleagues at the university saying, hey, we'd like you to come back in because some of your code stopped working. And my mom thought, that's strange because I wrote pretty good code and it's been pretty bulletproof for a while. So she went back in and looked at the code, and sure enough, nothing was wrong with her code. She had just put in a check many years earlier saying, if this code is still running as of such and such a date, it's time for somebody to have a look at it. Okay, so that's my mom. But the moral of the story is not just that my mom is awesome, which she is, but also that code that's written to run on top of database systems often persists for a very long time. Think about it. The information that's being stored may have value for a significant amount of time. And the systems that generate that information often are doing critical functions like letting students register for class and assigning them grades. You don't change that code all that often. What does change? Well, a few things. Computers get faster. Computers get bigger. They get distributed over more machines. Data grows and gets distributed over more disks. Workloads change. So in addition to the programs that get written in the past, new programs are written running against that very same data that require the data to be organized with new indexes and new partitioning to support new workloads in addition to the old workloads. So it's real hard to get rid of old database code. It tends to continue running over time. And that means you really want the kind of data independence that was developed as a concept to support these kinds of applications. And what's interesting to me is that this concept isn't true only for databases anymore. It's true in a lot of scenarios. This little anecdote leads me to an inequality that I dubbed Hellerstein Zin Equality, which I think is increasingly important to recognize in modern computing. But it's born out of this idea of data independence in databases. The basic observation is to look for scenarios where the rate of change of applications is much slower than the rate of change of environments. As I said from my mom's anecdote, that's true with database applications. They change very slowly. But in a lot of modern environments, the right-hand side is changing very, very quickly. Think about things written over, say, mobile devices or scenarios where you get surge crowds in systems, right? The rate of change of your environment and of your workload can be enormous and very fine-grained. And so some of the lessons of data independence that were invented for databases long ago are really important today in environments where you have enormous variability in workloads or in the environment on which you're computing, whether that's a network fabric or a cloud data center that's expanding and contracting quickly. In those scenarios where you see Hellerstein Zin Equality holds, think about how you can separate layers of your system and provide independence between those layers, where specifications are at a very high level in some sort of declarative style language, and adaptation can be happening at the lower level very quickly without changing the code that's running above. Very interesting and useful theme in computer systems that's going to be increasingly important going forward.